In this next section, there's actually a lot of definitions if you were to read through the book section or to go through the publisher's explanation of this section, this 1.2 types of data. And when it comes down to it, there's really only 3 sets of definitions that you need to understand in order to be successful in the homework and in the rest of the class. The other definitions that are present in this section I'm not asking you about either in the homework or on the exams, because there's no reinforcement of those definitions as we move throughout the textbook. But these ones are very, very core. And so let me define some things for you. Using Jensen language. So there's going to be language that's in the book, right? The Triola definitions, and there's others that you can read. I'll just give you my definition of a population. A population is everyone you want to make a statement about. And it could be everything, right? So if I wanted to find out the average weight of a quarter, well, my population is every single quarter that's been minted. It is not practical. In fact, it's impossible as quarters keep getting minted for me to get my hands on every quarter to weigh it. And so I'm not going to be able to get to that population. If I'm talking about the average age of the 25 students in my class right now, in our class right now, I could get all of your ages through admissions and records, right? All 25 of them. I could reach out and actually get the whole population. So what's the population in that case? It's every single student in our class. Only 25. So pretty easy to get that information, especially since it's part of your registration process to share that with me. Well, not with me, but with the college. I don't know. And I'm sure they wouldn't give me individual data, but they might give me summary statistics. And so a sample is some subset of the population. So when we get our sample, right, when I get my sample of quarters, I want to select them randomly. When I get my sample of people, ideally I want to get them randomly. But it's some group that you can get your hands around and get some data from. And so you'll look at some situations potentially in the homework, and they'll ask you, is it a population or a sample? More important, though, is that we understand this definition that's related. Parameter versus statistic. We often use the word statistic wrong, right, in our day-to-day conversations. A parameter is a measurement, a numerical value, right? I'll put a numerical measurement. Obtained from the entire population. And a statistic is a numerical measurement obtained from a sample. So the parameter is perfect. It is the perfect measurement. There is no error at all in a parameter because you used everybody. So if I went to admissions and records and say, take my 25 students and run their average age, and when they use all 25 of your ages, that's a parameter, and I got the perfect average for our class. Now, if I was using our class as a sample for all Stat 300 courses, then it would be a statistic, and it would not be perfect. There'd be some error in that, and that'll be a big part of our latter portion of the class in Chapter 7. But a parameter is a perfect value. A statistic is an approximation, and it can be a really good approximation, right? It could have little error. What could we do to control that? More and more people in our sample. Obviously, that would work out. But then other things will take its role as well that we'll learn throughout the course. But what's important right now is that a parameter is obtained from the entire population and a statistic is obtained from a sample. Okay, so I'm going to give myself a little bit more room to make another set of definitions, but while I do that, I want to talk to you about maybe some kind of statistics that we miscall statistics, like maybe a basketball player's free throw percentage. We often call that a statistic, hey, a basketball statistic, but it's actually a parameter because they are using every single time that person is up at the free throw line. And therefore, it is a parameter. If they were taking just a scattering of those, it would be a statistic. The last set of definitions is discrete data versus continuous data. And again, there's definitions in the book that you can read for other reinforcement. If I were to tell you what discrete data is, this is finite or countable data. And I guess I got to be a little bit more careful than that. And so we'll describe it along the way. Continuous data is data that can be continuously broken down. And let me give you some examples of those. I'll push these other examples down a little bit farther. Okay, let's take the example of this one. We want to find the average number of hotel rooms in Sacramento hotels. By collecting the number of rooms from each hotel. Okay, if we think about that for a minute, what are they? The question is the data discrete data or continuous data? Well, what is the data? What is hotel number 1 going to say? Hotel number 1 is going to report a number like 128. Hotel number 2 may say 250 rooms, right? Hotel number 3 may say 335 rooms. It doesn't matter. But what they're going to report are these whole numbers. That's what we mean by finite or countable. So let me just put up a scenario. Is there anything between a hotel saying 250 rooms and 251 rooms? Those are two practical things that could be reported. Is there any possible way that a hotel is going to call us and say, I have a number in between those two? And the answer is no. There's a physical count of those rooms, and therefore this is discrete data. Discrete data has a definite, if you're here, this is the next one. That's the other way to think about it. If you have 128 rooms, one hotel is reporting that. What's the next highest number that somebody could report? 129. It's absolutely known. No question about it, 129. That is discrete type of data. If you want to know about continuous data, that would be something like finding, collecting the weights of individuals in Stat 300. Now, as you think about weights, everything's done on the theoretical level. Is there anything between somebody reporting 189 pounds and 190 pounds? And the answer to that is yes. Somebody could report 189.5. Is there anything between 189 and 189.5? And the answer is yes. There's a bunch of things. There's an infinite number of things, but I'll go right in the middle. Is there anything between that? 189 and 189.25. 189.125 if I keep going right in the middle. How long can I play this game? Forever. If I have 189 pounds, what's the next weight? If you say 190, I'll say no. What about 189.5? If you say, oh, okay, 189.1, I'll say, well, what about 189.01? And we can play this game forever. That's what I mean by can be broken down continuously. Now, this is Jensen language, this is my language, a practical language, but one that I think will help you understand. So let's park that for a minute and come back to our definitions. Let's remember that a parameter is a numerical measurement obtained from the entire population. A statistic is a numerical measurement obtained from a sample. And let's come right down here to our first example. These examples right here are asking whether we have a statistic or a parameter. A recent California health survey included 2,799 adolescent residents of California. Okay, is that a parameter or a statistic? Is this a population or a sample? And this, actually, that may be the question. For that one, it may be whether something is actually, it's still a statistic or a parameter. Is the information we're going to get from this a statistic or a parameter? Well, there's way more than 2,799 adolescents in California. So that must be a sample of them. So this is a statistic. If I read the next one, a study was conducted of all 2,223 passengers aboard the Titanic. If they get any information, numerical measurement from that, that is going to be a parameter. How is it a parameter? They talk to all the passengers. So if you're looking at everybody, that's a parameter. If you're looking at part of it, that is a statistic. Now, somebody might say, well, I don't know how many adolescents there are in California. Well, that's why they chose a number so drastically low. We have a population that is super huge, right? And so there's got to be way more than 2,799 adolescent residents in California. And so you're going to answer some questions that way in the homework. And in the homework, you can get it wrong and know it's the other, and there will be some explanations in there, but you're welcome to ask me as well. If we look at this next one, they're wanting to know whether it's discrete or continuous. And that actually for the last ones that we have here. So remember what discrete is. Discrete means if you know one thing, you can name the very next thing. Or there's well, let me just leave it at that. And continuous means, well, you can't name it. It goes on forever. So here we're dealing with heights. Well, let's pick a height, like 74 inches. What is the height right after 74 inches? Let me not use that terminology. 74 inches. What is the next height after 74 inches? Not 75 because there's 74.5. Not 74.01 because there's 74.01 and 0.001 and 0.0001. We can play that game forever. This thing's continuous, right? How about this one? The clerk of a U.S. House of Representatives records the number of representatives present at each session. Well, let's suppose that there's 27 present at today's session. What is the next number of present representatives we could have? Absolutely 28. No doubt about that. There's no 27.5 representatives or 0.01 representatives. This is discrete. And hopefully that makes sense as well. And there's worked examples in the book. But a student wants... I want to put a third example in here because sometimes I'll have students walk away that says, okay, whole numbers, it's absolutely going to be discrete. Decimals, it's going to be continuous. And that's not necessarily the case. That's why I have this last example. If you consider the price of a textbook at the bookstore and you want to record the price of each text, well, let's just make up a price. They're expensive, so I'll put $128. Is there the next price after $128? And I'll have some people say, well, no, Jensen, because it's not 129, it could be 128.50, and you can play this game forever. And where they're making their mistake is you cannot make this game last forever. If you consider $128, there is a very next price, 128.01. We have a limit to the change that we can make, and because of that, there is a finite cutoff for this. So the price of a textbook, that type of data, is absolutely discrete. It is finite or countable. Okay, and so this is the way you're going to go through this 1.2 homework, and I think it'll make a lot of sense. But if anything doesn't, just let me know, either in the Zoom sessions or via email.